Hello, Applied Physics students. This is Mrs. Kremschreider, and I am going to kind of give you some notes. So the tags, the text activity guides that I'm going to give you, those are for you to read the textbook and answer the questions, and I'll provide you with keys for those. I'm just going to ask you to, maybe in a notebook, start taking notes and just write those down. And these are just kind of, again, making sure that you have the highlights and you've gotten the highlights out of your reading. So we're going to start by talking about section 2.1, which was titled Force. And we kind of have a definition of a force here, which is a push or a pull. So in fact, as you write, you are exerting a force on your pencil because you're pushing and pulling your pencil. And a force is needed to change an object's motion. Now, one of the nice things about learning physics is oftentimes this is stuff that you actually already know, you just haven't thought about it, right? I mean, you know this, right? If you're driving a car, right? Many of you are taking driver's ed or going to take driver's ed soon, or you already have a driver's license, right? When my car is moving and I want to change its motion, I have to use my brakes and exert a force to stop my car. When my car's at rest and I want it to move, I have to exert a force, okay, by pushing my foot down on the pedal and causing my tires to move. So again, you're familiar with this idea that forces are pushes or pulls. You do this all the time. Okay, balls that you throw and such. So a force is just a push or a pull. Motion then. There are kind of two types of motion. Okay, realistically, a motion, we can kind of say that the object may be at rest, in which case we typically would say that there's kind of no motion. The other way we can have motion is that our object can be moving uniformly, which just means kind of constantly or at the same speed in a straight line path. Okay. So we can have objects that are not moving, in which case we say that they are at rest. Or we can have an object that is moving. And for us in physics, we're going to talk about when our object is moving, that it's moving uniformly, which kind of means at a constant speed in a straight line path. So net force was kind of one of the little subtitles in your textbook. Okay. And we'll start again by kind of jotting down what the definition of net force was. Net force is the combination of all forces acting on an object So again, forces are still our pushes or our pulls, okay? But this is taking into account all of those pushes or pulls acting on an object. The net force on an object is what changes its motion. So it takes some sort of net force for an object to change its motion. And we're in physics class, so we're in a science class, so force is measured, oops, that's a C, in newtons, which is just our scientific term for force, or the unit that we measured it in. and a Newton is abbreviated with a capital N. So to take a look at some examples of this net force idea, if I have my object here, and I'm just going to make it a square little object because that's easy to draw. If I have an 8 Newton force acting to the right and a 3 Newton force acting to the right, the net force on this object would be 11 newtons to the right and that would mean that this object moves to the right. So kind of notice here that if we're trying to figure out our net force, right, so to calculate net force, if the forces are in the same direction, like they were in this instance, we add the forces to get that net force. So because the 8 Newton and the 3 Newton force were both acting to the right, we added those together to calculate our net force. So that's one example. We're going to look at 3 examples. So here's another object, and one of the nice things about the notes being video is that if you need a little bit more time to write or something, you can always pause, right? So here's my object. I have an 8 Newton force acting to the right, and I have a 3 Newton force acting to the left. So now my net force here isn't going to be the same, okay? It's going to be 5 newtons to the right, and it's to the right because my 8 Newton force is my larger force and it's acting to the right. Again, how would this object move? This object moves to the right because the net force is acting to the right. Okay? So again, we kind of want to notice how we actually calculated our net force, right? This time, if those forces are in opposite directions, notice that we subtract the forces. Our last example we're going to look at, again, here's my object, okay, and I have 2 newtons acting to the right and 2 newtons acting to the left. Now, my net force would be 0 newtons. That means that our object is not moving. Because there is no net force on it, our object cannot be moving. And we still calculated our net force the same way, right? These were in opposite directions, but 2 newtons minus 2 newtons equals 0 newtons. Okay? So those are a couple examples of net forces for you. Okay? The next section in our book is called Tension and Weight. Wasn't a whole lot in this section. They just do give us a little bit of a definition of what tension is, which is a stretching force. And an example of tension is a spring in a scale. And they had kind of example of that in your textbook. Okay. We also have tension in ropes when we have something that's hanging by a rope. There's tension in the chains or the ropes of a swing, for example. So we're introduced to this concept of vectors, and I don't know if you like the movie Despicable Me, but in the Despicable Me movies, the very first movie, the bad guy's name is Vector. And he names himself Vector because he says that he has magnitude and direction, which is the definition of what it means to be a vector. So the people who wrote Despicable Me were kind of showing off their knowledge of science. So a vector is defined as an arrow that represents the magnitude, which is just a big word for the word size. So magnitude just means size. And direction of a quantity. And quantity is just another way of saying amount. So what I drew here, okay, this is a vector. This is a vector. This is a vector. Okay, so those were all vectors. Okay, they are arrows that represent the magnitude or the size and the direction of a quantity, the amount. Okay. So, again, the kind of important part here, okay, is this idea that a vector has both magnitude and direction. A vector quantity is a quantity, and again, or amount, that needs both a magnitude, which again is size, and direction, for a complete description. Force, which is what we've been talking about, is a vector quantity. So forces always have a size and a direction. Okay, so forces are a vector quantity, which means forces have size and direction. And again, that was represented back here with 3 newtons and an arrow to the left, 2 newtons and an arrow to the left, 2 newtons and an arrow to the right. Okay, so I indicated their size by giving them a number and their direction by the direction that the arrow was pointing. So force is a vector quantity. Not all quantities are vector quantities. Some quantities are a scalar quantity. A scalar quantity is a quantity or amount that can be described by magnitude, which remember again means size only. Okay, so scalar quantities we can say that they don't have direction. So scalar quantities are a quantity that can be described by just a size, a magnitude. They don't have direction. Some examples of scalar quantities are time, area, and volume. Okay, speed is also a scalar quantity. So section 2.2 is called mechanical equilibrium. And the definition of mechanical equilibrium. Oops, 2 C's in there. Sorry about that. That didn't work very well. Is that it is a state wherein no physical, I did it again, sorry, not spelling very well, changes occur. You can also say that mechanical equilibrium is a state of steadiness. And we are in mechanical equilibrium when the net force on an object is 0. Okay. The object is in mechanical equilibrium. So we kind of go back to those pictures I drew, right? This object here, this would be in mechanical equilibrium because the object is not moving. You also can have moving objects be in mechanical equilibrium. It just means that they have to be moving at a constant speed and in a constant direction. There's something called an equilibrium rule. Which says that the net force on an object is 0. Okay. Mathematically, and remember we are going to be doing some math in this class. This looks like this. This symbol is the Greek letter sigma, and it means sum of. So you might see it throughout physics, and it always means sum of. The F stands for forces, is equal to 0. Section 2.3 is about the support force. And the definition of support force is the upward force that balances the weight on an object on a surface. So, for example, I'm writing these notes on my iPad. my iPad is being supported by the table that I'm sitting at. And that is what is keeping my iPad from moving downwards due to gravity. Okay, so that support force is this upward force that balances the weight of an object on a surface. Because, right, if I just held my iPad out and there wasn't a table underneath it, it would fall. So what's keeping my iPad from falling as I'm writing on it? The fact that there's a table there to support it. So that table is the support force, providing the support force that is balancing the weight that would pull my iPad down. Okay, support force is often called the normal force. Support force also, we can say that for an object at rest on a horizontal surface, the support force must equal the object's weight. So if you're taking these notes in a notebook that's sitting on a table or on your lap, right, that table or your lap is providing that support force that's equal to the weight of that notebook. So to kind of take a look at this, right, if I have my object sitting on a table, right, fancy drawing, there is gravity acting downward on this object, but there is also a support force provided by the table that's acting upwards. And that's why that object is not moving in a vertical motion. It's not moving up or moving down, right? Now, if this object was moving up, that would mean that the support force is more than gravity. If this object was moving down, it would mean that the gravity is more than the support force, right? So the funny videos you've seen, right, of somebody sitting in a chair and it breaks, right? That's happening because the chair is not able to provide enough support force to counteract the gravity or the weight of that person sitting in that chair. Okay, so again, when my support force and my gravitational force are equal to each other, my object is not moving, right? And that means it's in mechanical equilibrium. Because remember, when the sum of my forces is equal to 0, my object's not moving and I have mechanical equilibrium. The last thing I want to look at then are the page 16, the two little think questions that were in here. So the page 16 think question reads, consider the gymnast above hanging from the rings. If she hangs with her weight evenly divided between the two rings, how would scale readings in both supporting ropes compare with her weight? Right? Well, first off, the scale readings would equal her weight, right? And if her weight is equally supported between each of the ropes, which it says that it is in this case, each scale would read half of her weight. Suppose she hangs with slightly more of her weight supported by the left ring. How would a scale on the right read? So still, when she's not equally supported, the scale readings are still going to equal her weight. The difference being now, because she has more of her weight on the left than the right, the left scale will read more than the right scale. So let's say she weighed 100 pounds, okay? Up in this first instance, if she weighed 100 pounds, each scale would read 90 or 50 pounds. In this second circumstance here, okay, if she has more of her weight on the left than the right, that she's hanging unevenly, okay, then maybe the left one would read 80 pounds and the right one would only read 20 pounds. The scale readings still are going to add up to her weight. So that was the page 16 think questions. We also want to take a look at the page 17 think questions. And there are 2 of them there. The first one, what is the net force on a bathroom scale when a 110-pound person stands on it? Well, that object, that scale, isn't moving, right? So the sum of the forces has to be equal to 0. It has to be in mechanical equilibrium. Okay? So the net force is 0 because it's not moving. The second think question there says, suppose you stand on 2 bathroom scales with your weight evenly distributed between the 2 scales. What is the reading on each of the scales, right? Again, the readings together are going to equal the weight. If my weight is equally divided between the 2 scales, each scale is going to read half my weight. What happens when you stand with more of your weight on one foot than the other? Again, still the total of the readings on both scales, when I add them together, are going to be equal to my weight. But if I have more weight on one leg than the other, then the scale with more weight will have a higher reading. And the scale with less will have a lower reading. So again, that idea that being that maybe I have like 80% of my weight on one leg and 20% on the other, and I weigh 100 pounds, then one scale would read 80 pounds and the other scale would read 20 pounds. They're still adding up to the weight of the person. So those are your little notes for the first 3 sections of Chapter 2. Have a good day. I will talk to you tomorrow.